NCERT questions of P block, boron and carbon is what we are going to talk about in this session today. This is Shishir Mittal from Vyas certification, and block chemistry presents a very interesting perspective of the entire inorganic chemistry. As a matter of fact, boron is at the heart of entire P block. So let's begin. Discuss the pattern of variation of oxidation states of boron to thallium, and there's a B part also. Carbon to lead, boron to thallium and carbon to lead. What is the variation in oxidation state? This has been asked. We are supposed to mention that and discuss that. Let's discuss. If you just write down the important points, you would notice boron, aluminium, gallium, indium and thallium. Now, oxidation state typically of boron, typically the oxidation state of boron is +3, +3, +3, +1 and +3, +1 and +3. Boron also shows a rare state of -3, which is not shown by others. Why? Because boron is a non-metal, while aluminium to thallium are metals, and metals never show oxidation state which is negative. So, -3 of boron is visible only because boron happens to be a non-metal. This is one variation. Everybody is showing +3. Why are they showing +3? They are showing +3 because they have 3 electrons in outermost orbit, Ns2np1. This is the general configuration of group 13. And since these 3 electrons can be lost, they all show a common oxidation number of +3. However, as you move down, you notice that indium also begins to show a state of +1. Although +3 is more stable for indium, still it does show +1. And in case of thallium, it is +1 which becomes more stable as compared to +3. Wow, why? There is a very unique thing called as inert pair effect. It so happens that 6s2, 6p1, now 6s2 electrons in thallium become somewhat inert and they are no longer interested in formation of bonds. Is it a similar trend in carbon to lead? Let's take a look. When you talk about carbon, Kartik, Shri Ganesh, Shankar Parvati. There's a shortcut to remember the family, the entire Shiva family you can say. Carbon, it does show +4, +4, +4. We have +2 and +4. We have +2 and +4. Carbon actually shows a number of different states also. Like silicon could be, carbon being an organic, the source of organic chemistry, carbon can show all the oxidation states from +4 to -4. So carbon is a very unique element in that sense. Silicon and germanium are metalloids. Along with +4, they also show -4. Tin and lead are metals. Because they are metals, they never show -4. However, they are capable of showing +2 state in addition to +4. In case of tin, +4 is more stable than +2. And in case of lead again, +2 becomes more stable than +4. Some answers are very similar. General electronic configuration is Ns2np2. When both the S and P electrons are lost, 4 electrons are lost, and that is why a common oxidation state of +4. As you move down, the stability of lower oxidation state increases. So, carbon, silicon and germanium, for silicon and germanium, +2 is so unstable that it does not even exist. Tin, +2 begins to show up, although +4 is more stable. Only in the case of lead, that is 6 period, you have 6s2, 6p2 is the electronic configuration. You find that 6p2 is lost easily. 6s becomes inert. It is relatively more stable. Okay, wow, that's very interesting. Yes, that is very interesting. Now you find that, I repeat, carbon does show rare other states also from +4 to -4, actually carbon can show multiple fractional states also because of millions of organic compounds which carbon can make. But again, these are the trends. Now, can we explain the trends and anomalies? Inert pair effect, yes, it does remain. I'll talk about that. But other than that, metals do not show negative states. Metalloids and non-metals can show negative. That is why -4 for them. And carbon has a special status. It can show various different states. Why? Because it forms millions of compounds in form of organic compounds. Due to catenation property, it forms a large variety of compounds. And because of that, carbon can show really numerous oxidation states. So we have explained 3-4 points. Negative states of boron, carbon, silicon and germanium, that is one trend. Fractional states of carbon, that is the second thing. Third thing is indium and thallium, tin and lead, they start showing lower oxidation states also due to inert pair effect, and only in sixth period you find that the lower oxidation state actually becomes more stable than the higher state. Why? We say that in each case 6s2 electron, has become inert. Why do we say it has inert pair effect? Can we explain inert pair effect also? Yes. What we can say is this: down the group, size increases. 6s is a huge orbital. It's large in size, and because it is large in size, electrons don't repel as much, and they are reasonably happy because they are spread over larger volume. They are more stable. Not just that. Number one, electrons are more stable on their own. Plus, if you involve them in bonding, if you involve them in hybridization, what you find is this. This is ground state. And excited state is this. Just watch. You make one electron jump and you get excited state. And then this excited state undergoes hybridization 1, 2, 3, 4. Then you have sp3 hybridization, and then you find 4 bonds being formed. This is typically in group 14. I'm talking about group 14. Similarly, you can talk about group 13 also. You just take just one electron off, excitation, and then you can have sp2 hybridization in group 13. Now, this excitation involves some increase in energy. From 6s, if the electrons have to be excited to 6p, you have to give some energy. What is the advantage? The advantage is instead of 2 bonds, now you can form 4 bonds. Down the group, bond length increases, yes. Because bond length increases, bond strength decreases, yes. If the bond strength is less, and if that extra, you are forming extra 2 bonds in this case. In case you show excitation, you get 2 more bonds to form. Usually what happens is with higher up ones, carbon, silicon, germanium or boron, aluminum, gallium, more number of bonds means more energy is released. This is profitable business. Down the group, size increases. Bigger size means longer bonds means weaker bonds. The bond strength decreases. So, moving down the group, bond strength has decreased. Yes. At the same time, excitation becomes more difficult because 6s electrons are very happy. They don't want to get excited to 6p. So, excitation keeps on becoming more difficult, and after excitation you can form new bonds, but new bonds are no longer as profitable. So you find that lead and thallium in 6th period do not discover sufficient motivation or profit in this excitation and forming 2 extra bonds. In excitation you have to give energy, in 2 bonds you get more extra energy released. Investment is more and release is less. They don't like it, and that is why you have the so-called inert pair effect in which 6s2 electrons don't much like to participate in bonding. And that, my dear, is the reason why the stability of lower oxidation state increases on moving down p block. I have mentioned this in reasonably good details. We have mentioned 3-4 points. Number 1, why common oxidation state of +3 and +4? 1 point I have told. Second point, why negative states for a few? Third point, why fractional for carbon? And fourth point, the inert pair effect statement. Fifth, also the logic or the reason of inert pair effect also we have mentioned here. And I hope this is very useful to you. In case you want a very regular answer, this is the answer. You can take a screenshot. But then what I have told you verbally is a much superior answer.